All right, so we're going to be finishing up the rest of 2.3 here. So back yesterday, we met all together because, weather was fine. We went through some basic ideas of like better ways to find a limit, right? So previously, we've been dealing with limits where we were kind of doing approximations. So we're plugging in different values of x, getting closer and closer to the number we were trying to approach for x. So, we said, for example, the limit of x goes to 5, we would test numbers getting closer and closer to 5. So we do like 4.5, 4.9, so on and so forth. We had a left hand limit. We tested things on the right hand limit to see, does it really approach this? Now, yesterday we looked at better ways to do this where we can say, hey, if I was doing the limit of x approaches 5 of 2x minus 3, we pretty much came to the conclusion that we can take this number that x is approaching and just substitute in for x. And so this limit would really be equal to 2 times 5 minus 3, which will give you an answer of 7. And this is 10 times faster than the other way, right? And the way we're able to do this is we had some limit laws, right? So we looked at how the limit laws were and how we can use them. And essentially, using the limit laws, we can split this up into two separate limits, and the 2 multiplies the limit of x, and so on and so forth. And this is pretty a quick, handy, easy way to try to find a limit. However, we did run into some cases where we tried finding a limit of something that did not exist. So, for example, let's say we did the limit of x approaches 1, and we had the fraction x squared minus 1 over x minus 1. If we try plugging into here, we run into the issue of getting 0 over 0 if we evaluated, and that doesn't really work too well, right? So if I try to plug in 1 into both these x's, we get 0 over 0, and that's undefined, okay? So we came up with an alternative solution, which is, hey, we can factor this, because we know this is a difference of squares. And then through factoring, we can simplify this to be a new function. And we went over the rule that, hey, if this function is really equal to this function, then we could rewrite the inside to be this, x plus 1, and this allows us to take the limit of this instead. So instead of kind of getting this undefined result, we can rewrite our limit to something easier to find, which is this. This gives you an answer of 2. So that's kind of what we talked about yesterday. Now, there were 2 other examples that are a little bit more complicated, right? Because this is only one type of function you can have where we have an issue trying to plug in for the limit. We had some that can have radicals. We have some that have a bunch of fractions. So you're going to see a variety of those. This is the nicer one of the 3, but you could technically see all 3. So you want to make sure you're comfortable with factoring things. So that it's doing like difference of squares, cubic factoring, regular quadratic factoring, all the fun stuff, GCFs. That's kind of one type of problem. Then you have the weird fraction problems, where there's fractions and fractions, and then you have the what if we have a root problem. Okay, so you want to make sure you are comfortable with all 3 of those. Now, what we didn't get to cover is something called the squeeze theorem. Okay, so the last thing in 2.3 we're going to go over is the squeeze theorem. Essentially, it kind of is similar to how this idea works. So we said how, if this can be simplified, we can use that instead. It kind of has a similar idea, but instead of looking at like simplifying, we're saying that a function is kind of squeezed between 2 other functions. Okay, so we can take a look at that and see kind of how it works. It's kind of interesting. It's used for a couple proofs that are important for some other concepts we're going to talk about. So like we're not going to be like looking at the squeeze theorem like a ton, but this concept and this idea is used to make other things work in the course. So this is a pretty important one. Okay, so we got the squeeze theorem. Squeeze theorem. So for the squeeze theorem, essentially it works like this. So if we have some function g of x, it's less than equal to f of x, which is less than equal to h of x. So essentially this function f is squeezed between g and h. So f is in the middle, right? So h is kind of the upper boundary, g is the lower boundary. So sometimes they might be equal, but sometimes f is a little bit smaller than h, but there's also times f could be bigger than g, okay? So if this is true, and we know that the limit as x approaches a of g of x equals the limit as x approaches a of h of x, so these two limits are equal, and let's say it goes to L. So if we have the limit of g is equal to the limit of h at a, and we get the result of L, then, and here's the squeeze, if these limits are equal, it squeezes f to have the same limit. Okay, so then the limit is that same limit of x going to a of f of x will have to be equal to those results. Okay, that's the squeeze theorem. So the squeeze theorem works if f is in the middle, is squeezed between g and h, and the limits of g and h are equal, it forces the limit of the middle term to be equal to the middle function. So if our ends have the same limit, then the middle has to have the same limit. Hence, squeeze. We're kind of squeezing it in, right? So we're kind of forcing the ends to be the same, which makes the middle the same. Okay, so that's why we have the squeeze theorem. Now, we're going to do kind of two examples here to kind of show off how the squeeze theorem works. The first one is going to be, we have to get a little, our thinking caps on to think how it works. The second one's a little bit more straightforward. Okay, so we're going to do two different examples here using the squeeze theorem. So, example 1 for the squeeze theorem. Let's say we have the limit of x goes to 0, and what we're trying to find the limit of is x squared times sine, this is the trig function sine, of 1 over x. Now, using what we did yesterday, if we try plugging 0 in, one would assume this limit would be 0, but here's the issue though. If I plug 0 in, we're dividing by 0, so this would technically be undefined. Okay? So this is a case where we can't just evaluate. So we kind of have to use the squeeze theorem in a certain way to kind of show what this will be equal to. Okay? Now, the way we kind of do something like this is we notice that if we're kind of looking at, why is my thing not showing up anymore? All right, whatever. So if we're looking at both parts here, we have x squared, okay? We also have sine. These are two separate functions multiplying each other. Now, what is interesting is sine does have an upper and lower boundary, right? So we think back to your days of geometry, okay, or trig. Sine can be no more than 1. It can be no less than -1. Okay? So we're going to do the work over here. So essentially, sine itself, and then we're doing of 1 over x, has an upper boundary of 1 and a lower boundary of -1. Okay, this is true. Okay? Sine of any angle is going to be capped with an answer of 1 and has a lower cap of -1. Okay, so this kind of sets up the squeeze. Now here's the thing though, right? We should have a function on either side, and we need this to be f of x. Right now it's missing the x squared, but we can easily fix that, right? So what we're going to do is we're going to go ahead and multiply this whole thing by x squared. So we're going to take x squared here, times it in, x squared here, times it in, x squared here, times it in. What that's going to allow us to do is we can take this sign kind of fact and we can manipulate it to look more like our limit. So if we do that, we get negative x squared on the left. The middle will be x squared times sine of 1 over x. And the right side would be positive x squared. Now, if we did this correctly, what we should see is that this whole thing is now in the middle between two functions, which is kind of like our squeeze theorem, right? We have our x squared times sine of 1 over x. That's our f of x now. The left side is negative x squared. The right side is positive x squared. And what we can do is if we take the limit of all these pieces, we're probably going to get the limit to be equal on both the left and right side. Okay? So if we do this, we can say this limit as x goes to 0 of negative x squared. And again, I'm using the same limit that I have here in my question. So I'm going to say the limit of the left side is going to be less than or equal to the limit we're trying to find. Okay, this is the important part here. This is the limit we're trying to find, right? This is where we started with, right? That's over here. It's going to be less than or equal to the limit as x goes to 0 of x squared. Now, what's nice is using our shortcut method, right? I can just plug 0 in and we get our answer, right? Because we're not undefined. So as the limit of x goes to 0 is being taken of negative x squared, we just get 0 on the left side. Then we have the limit that we're trying to find that we don't know how to do yet. And that's going to be less than or equal to this limit, which is the same thing. If I have x approaches 0 and I'm looking at x squared, we plug in 0. 0 squared is 0. Okay, and then we get this result. And what's interesting about this result is the left side and the right side are equal, which forces the middle to be also equal. And this is the squeeze. Okay, so when we take the limit of all three pieces, the limit in the middle we don't know, that's what we're trying to find, but we can find the limit on the left and right side and it squeezes the limit in the middle. Okay, because since these are inequalities, they're equal to, so this 0 is less than or equal to the middle, which is less than or equal to 0, that forces them all to be the same. Okay, and so essentially, our limit would be equal to, do it here, be equal to 0. Okay, and this is from the squeeze theorem. Now, in this particular case, we had to build the squeeze theorem to work, right? We didn't really have it set up. So this is kind of a little more of a advanced question, okay? But this is kind of one of the ones where you feasibly can set it up, and that's because sine kind of has this 1 to negative 1 correspondence, not correspondence. It has this negative 1 to 1 kind of range, all right? And so cosine can do the same thing. So if I gave you cosine instead of sine, we could do something similar. Okay, so you have to have a function that does have a kind of like a closed interval when it comes to its possible answers. So there could be sine, could be cosine. Okay, there's not many, but this is one we can kind of set up on our own. Now, you're not always going to have a question where you have to build it from scratch. We do have an example here where it's already provided for you. We're going to do that next. Okay, so what that kind of looks like is this. So if we were doing that next one, this is example 2. So example 2. So it says if we have 4x minus 9 is less than or equal to f of x. So we don't really know what f of x is. It's something, but we know that the lower boundary of f of x is bounded by the function 4x minus 9. And the upper boundary is x squared minus 4x plus 7. Okay, so we know this is true. And we know this is where x is greater than or equal to 0. We need to find the limit of x going to 4 of f of x. So this is what we're tasked to do. So we need to find the limit of f of x as x is going to 4. Now the best way we can do that is if we can find the limit of the left and right sides. Hopefully they're equal, right? Because if this limit on the left is equal to the limit on the right, then the middle has to be the same. So we're going to hope that if we do this limit, that the squeeze theorem is going to apply, right? Because the squeeze theorem only applies if the limit of the left and right side are equal, and it forces the limit of the middle function to be the same. So let's try it out. So let's do left side first. So limit as x goes to 4 of 4x minus 9 is less than or equal to the limit of x going to 4 of f of x is less than or equal to the limit as x goes to 4, this time of the function x squared minus 4x plus 7. Alright, so let's look at the left side. Again, we have a nice equation. We could probably just plug in 4 and get away with doing that. So if we plug in 4, we get 4 times 4 minus 9 is less than or equal to our limit of the middle. Right side, same thing. We can plug in 4 and it's probably going to work because it doesn't look like we have any issues with things being undefined. So we'll plug that in. And what's going to happen is the left side becomes 16 minus 9, which should give us 7. So it looks like the limit of x going to 4 of f of x is at least 7. That's what the left side's telling us. The right side, we get 16 minus 16 plus 7. Well, that's also 7. So our limit of f of x as x is going to 4 is at least 7, but no more than 7. Well, then it has to be 7. So this is going to imply, this implies that the limit of x going to 4 of the function f of x is actually 7 itself. This is by the squeeze theorem. Okay? So again, the squeeze theorem essentially is your finding limit of something smaller than the function, the finding limit of something that's larger than the function, and then we want those limits to be equal. And as long as these limits are equal, then the limit in the middle has to be the same as well. Okay? This is called the squeeze theorem. So, if you really want to try one out for size, you have some different crazy ones. So if you want to try one as some practice, okay, so this is to do on your own. But if you want to try a problem kind of like number 1 to test out your skills, you can try this one. So cosine of x is less than or equal to sine of x over x. It's less than or equal to 1. This is a little tricky. Okay, this one's a little tricky. But if you want to try it out, you could try it out. And then we could talk about this in person if we have some questions about it. Okay, but this is kind of one that'd be kind of a little more difficult. Probably a little more harder than some of the ones you might see, but it'd be something to try if you want to kind of give it a shot. I'm missing one part here. We do need to know this. So the limit as x goes to 0 you want to find this. So you're going to find this using this thing. Actually, I'm looking at it, it's actually a lot easier. It's kind of more similar to 2. So you can try this one as a bonus question. It's kind of looks like 1, but it's actually set up for you nicely. You can actually just try to do the limit. So this is similar to 2. So if you want to try this one on your own, go ahead and do so. If you want to email me like the solution or something like that, I could take a look at it and make sure you kind of got it going good. Or we should be meeting on Friday. I think by then we should be okay. So if not, I could take a look at it before class on Friday. That's also fine. Now, we do have some time left here. So what we're actually going to do is we're going to press into 2.5 here. So we'll do that next. So that kind of wraps up 2.3. So again, the focus on 2.3 was trying to start thinking about finding the answer for limits a little bit differently. So instead of doing approximations using tables, okay, we were going more of a algebraic approach of like, hey, can we actually just plug in x? Can we simplify first and plug in? So at that direct substitution property, because that's like the key to this section. And then we even use direct substitution property here for example 2. That's what we did to kind of get the left and right sides to kind of form the middle. Okay. So essentially, when we come to finding limits, we're going to try to plug in numbers first, like the number itself, instead of doing a table. Okay. If we can. Sometimes you can't. So this brings us to this idea of continuity. So when we were doing the problems yesterday, sometimes we were able to plug in numbers and it worked, and sometimes we were not able to. And this kind of brings up this idea of continuity. Okay, so for 2.5 here, we're looking at continuity. So when are things continuous? Okay, so pull this up here. I want to take a look at. Okay. Cool. So when we're looking at 2.5, help actually have the marker. 2.5, and we're looking at continuity. Okay, so we're looking at continuity. Essentially, we want to know when a function is continuous. Okay, for something to be continuous, we usually look at graphs kind of like this. Okay. There's no issues in the graph. There's no open circles. There's no jumps. All those weird things. Okay. So usually in algebra, a lot of the functions we deal with are continuous, right? There's some that are not. And we've been dealing with some functions that are continuous and some functions that are not so far in this course. We haven't really talked about that per se, but we have been exposed to them. So we kind of need to figure out a good way to kind of define when a function is continuous, and does it have any implications on the limit, which it does. Okay, so we're going to start out with a definition. I'm going to do it over here. So we have a definition here. So f is continuous. F is continuous at x equals a, then there's 3 things that are true. So a, f of a exists. This is pretty important. This means that I actually can plug into the function. Okay, that means when I do the limit, I can actually plug it in. Right, we talked about that yesterday. B, the limit exists. So the limit as x approaches a exists, and then there's part C. The limit as x approaches a of f of x equals f of a. These are the 3 things you get. Okay, so if we know the function is continuous, you kind of get all 3 of these at the same time. The one that's kind of the most important, and I'll start here in magenta, is part C. This is what we're going to focus on a lot. So if we know the function is continuous, then I can literally plug a into the function, and whatever that equals is the answer, okay, for the limit. Because I know f of a exists, and the limit exists, and that specific limit is f of a. Okay, so part A and B have to exist for C to work, and that's always true if f is continuous. Okay, so this is kind of a big deal. Okay, now what that allows us to do is we can test to see if a function is continuous. Okay, so you can test literally every point, and as long as this works, then f is continuous. So what we can say is f is continuous. This is a side item here. So f is continuous on the interval a to b if continuous on all the values in the interval. Okay, so what this allows us to say that f is continuous in an interval, so from some a to b thing, then it's as long as it's continuous on all the values. So if we kind of go back to look at what we've been doing with this definition, okay, it's kind of like if I test every number from a to b, and this is always true, this limit always works, then the whole function's continuous on that whole interval. Okay, so things we can do, we can test for continuity. Okay, so the way we can test for continuity is kind of two ways you can do it. You can look at, like, if you're able to graph the function, it's usually the best way to do it, but we can test individual points. Okay, so we're going to do two examples where we test an individual point. We'll look at the continuity there, and then we're going to look at how can we tell when things are not continuous if we're not looking at a graph, okay? And what that looks like on a graph as well. So let's try some examples where we were testing continuity. Okay, so for example 1, we have the limit as x approaches 3 of 2 to the x. Okay, so what we're going to do is we're going to figure out, are we continuous on this function at 3? Okay, so we do this by plugging it in. So I'll do 2 to 3 to the third power. That equals 8. So it seems like it exists, right? So what we can say is the function two to the x is continuous, and you can just do cont, that's short for continuous, that's fine with me, is continuous at x equals 3. So this result, for example 1, tells us that we are continuous at this function when x is 3. Okay? Example 2. Let's say we had the limit of x going to pi, and the function itself is cosine of x. So if we try to make this work, again we plug it in. So we have cosine of pi. So again, testing your trig knowledge here. Cosine of pi is going to be equal to -1. Again, this seems to work. We're clearly defined there. So we are meeting the conditions for part C above. Okay, so since we meet the conditions of part C above, the function cosine of x is continuous at x equals pi. Now, technically both these functions are continuous functions anyways, okay? Meaning that no matter what x you plug in for example 1 or what angle you put in for example 2, this is always going to work, okay? But we can check continuity at points using limits, okay? Because usually what happens is when a function is not continuous, there's a particular point where something weird happens, okay? I told it not to give me notifications. All right, so it'll tell us essentially what's going on at a point, okay? Because usually at one particular value of x, there could be pretty much like 3 major things that could be happening. There's a 4th thing too that gives us discontinuity, okay? And essentially, if we look at our definition of continuity here, right, this part C here, we're continuous if this is true, so we're discontinuous if it's false, meaning, so you have the discontinuity, so we have a discontinuity when our limit as x is going to a of f of x is not equal to f of a. So this is when we are discontinuous. So our limit does not actually equal the function value. Okay, and this is when we're discontinuous. And we actually saw this yesterday. So we did those 3 examples where we couldn't plug in x. Those are discontinuities. Okay, now there were different types of discontinuities there. Okay, but those are examples of something that's discontinuous. Okay, because we can't plug in a. If you can plug in a, then we're continuous. So essentially, the only time we can do our little fancy trick of plugging into x, our limit, is if the function is continuous. If the function is continuous, rock on, you can do it. If the function is not continuous, we might have a problem. Okay, sometimes it can work, sometimes it might not. But we have a discontinuity when this is not true. So this is not true when there's a discontinuity. So what we're going to do real quick is we're going to go through the 4 different types of discontinuity, and we'll see if we can do some examples before we kind of hit some time limit. So there are 4 different types of discontinuity. One of them is kind of a catch-all, so we'll do that one last because that one's kind of dumb. But there's 3 main ones. First one, we have removable. So we have removable discontinuity. This is number 1. This is the first type of discontinuity, removable. So what does it mean to be removable? Okay, essentially removable discontinuity is where the left and right hand limits actually meet at the same place, but for some reason the function does not exist there. Okay, so here is the generalization. So the limit as x approaches a from the left of our function is equal to the limit as x approaches a from the right side of the function. So these 2 are true. However, they do not equal f of a. This is our first type. Now, what that looks like is something like this. Let's say this is your graph. This right here is x equals a. So as we can see, as we go to the left and go to the right, we're meeting at this open circle, but it's an open circle. So this is a removable discontinuity. It's almost as if someone literally just like cut it out of the line and just took it out, right? So if you took like a Twizzler and you chopped a section out in the middle, that's a removable, okay? So the limits meet up at the same place, but there's nothing there to meet up at, okay? Because it's an open circle. That's removable, okay? Option 2 is we have something very similar removable, but it's called a jump. A jump discontinuity. It's kind of like removable, but the limits don't actually line up. So here, the limit as x goes to a from the left of f of x actually does not equal the limit of x approaches a from the right side of f of x. So the limit does not exist. In option 1, the limit does exist, right? Because the left and right sides are equal, then the limit exists. The limit just does not equal what f of a equals. In 2, the limits are not even equal, so the limit does not exist. So an example will be something like this. So let's say we had, I don't know, a graph that looks like this. Make this a little bit better. Better dot. There we go. So as we see, the left side ends at this open circle, the right side ends at this closed circle, but they're not the same. This is a jump. Okay, so the graph jumps to another part of the graph. Okay, it's not continuous. They're not connected. Okay, they're disconnected through a space, like a gap, where it jumps. Removable is they're discontinuous at a single point. So it's close, but there's something missing in the middle. Here, they just don't even touch each other. They're not even ending up in the same place at all. They're like two separate areas. The third one that we saw a lot is infinite. So infinite. So in an infinite case, we actually have one of the limits going to infinity. It doesn't matter if it's the left side, doesn't matter if it's the right side, or both sides. One of them are going to infinity. Okay? So we can say that the limit as x going to a from the left of f of x is going to equal either positive or negative infinity, or you have the limit as x approaches a from the right side of f of x equals some positive or negative infinity. Okay? So this is going to be like when we have our asymptotes, right? So a good example would be our classic rational function where we have a vertical asymptote here that's at x equals a. Okay? And this is also at x equals a. These are the three main ones. Now, there are some times where we lack a lot of information and we can't really discern if it's removable, jump, or infinite. So we have our case 4. This is our catch-all. So this is like the, we know it's discontinuous. We know there's discontinuity, but we can't tell if it's 1, 2, or 3. So this gives us essential. I just define this as the other category. So essentially, if it doesn't fit the mold of 1, 2, or 3, but we know for sure it's discontinuous, it goes in option 4. I'm going to say catch-all. So if we know it's not in 1, 2, or 3, it's essential. Okay? So usually it's essential when we just know that it doesn't exist. Like the limit doesn't exist, but we don't really know why it doesn't exist. Like it doesn't really say that both of them don't line up for a jump. So it's kind of a weird one, but something you can see. So what we're going to do real quick is I'm going to give us... we're going to look at an example of like kind of all 4 of these. Okay, so we're going to see an example, and we're going to determine what is provided, if it fits removable, jump, infinite, or it's just essential. Okay? And that'll be the last thing we do. So this should be example 3. Okay? So we're going to do part A. So let's say we have the limit as x is approaching 2 from the right side of f of x, and we know that is equal to a positive infinity. Well, since we have a limit equal to infinity, we obviously have a infinite discontinuity. Okay? So if we're trying to figure out what kind of discontinuity this is, we have an infinite discontinuity. This one's probably the easiest one to identify because literally there's infinity in there. Okay? So kind of forces our hand. So that one's pretty easy. Part B. Let's say we have the limit as x approaches 2 from the left side of f of x equals the limit as x approaches 2 from the right side of f of x, and it equals 5, but f of 5 f of 2, my bad, f of 2 is no solution. So the question is, what kind of discontinuity is this? Well, if we look at it, looks like the limit and the left and right side are both approaching 5, right? So it seems like the limit as x goes to 2 from the left and the right side are meeting at the same place, but f of 2 is not 5. So this has to be a removable. Okay, it's not jump. If jump will be these two are not the same. So this has to be removable. Okay, so this would be a removable one. So this is removable. Okay. C. Let's say we have the limit as x approaches 2 from the right side of f of x, and we're told that it does not exist. D and E does not exist. So let's see. Is it removable? Well, no. I mean, removable discontinuities, the limit exists, right? Because the left and right side equal each other. So it can't be removable for sure. Now, 2, the limit does not exist. However, we know for certain that the left and right sides aren't equal. This doesn't really exactly say. It just says the right side doesn't exist. It's not infinite. So it's definitely not 1, definitely not 3. It doesn't really seem like it's 2. So we're going to say it's essential. Okay, so in this case it's going to be essential because it doesn't really fit all of them exactly. It seems like it might go into 2 a little bit, but we're missing a lot of information, so we can't really say for sure. So we're going to say this is essential. Okay, the essential category is weird because you just can't be in any other 3. So those are catch-all, so it has everything there. Okay, and then we got one more. So this is part D. So we have the limit as x approaches 2 from the left of f of x equals 3. And we also know that the limit of x approaches 2 from the right of f of x equals -1. So the question is this discontinuous, and what kind of discontinuity is it? Well, the left side's going to 3, the right side's going to -1, so we're not removable because they have to be equal. So it seems like it's a jump, right? It's definitely not infinity because there's no infinities here. So this seems like this has to be a jump discontinuity because our limits are going to 2 different places. Okay. For removable, the limits are meeting at the same place. There's just nothing there. For jump, they're meeting in 2 different places entirely. Okay, so it's a little bit different. Now, we're going to take a pause there for 2.5. Okay, but essentially the essence of 2.5 is we're trying to look at when is a function continuous versus when a function is not continuous. Okay, and it revolves around the limit. ironically, right? So if the limit of f of x as x approaches a is equal to f of a, so we can actually plug in a and get the answer for the limit, then it's continuous. If it's not, then it's not continuous, and that's what this is saying. Okay, so this is equal continuous, not equal discontinuous. Okay, and if it's discontinuous, we have 4 categories it can be. 99% of the time, you're looking at removable, jump, or infinite. Okay, essential is kind of weird, doesn't pop up a lot, but it's something you should be aware of. Okay. Now, what we're going to do next time, is what we'll do on Friday, okay, is we'll look at the last part of 2.5, which is called the intermediate value theorem, which is using continuity to kind of help us find an answer. Okay, so if we know that the function is continuous, we can actually find an answer using this kind of method of intermediate value theorem. Okay, so we'll kind of talk about how that works on Friday, but we do have the quiz on Friday. Okay, and so I was thinking about what that's going to look like. So essentially, I'm going to have one question that's kind of the second part of 2.5. So I'm going to give you a graph, and I'm going to have you answer some things about the graph. That'd be question 1. And then I'll give you maybe like 2 different questions with limits. I'll probably give you one where the limit's going to be a nice limit, where we can plug it in. And then maybe you have one limit that's not as nice, where if you try plugging it in, it's undefined. Okay? So it'll be pretty much like a 3-question quiz. 1 question with a graph, find all the pieces. Second question will be a nice limit, and the third question will be a not as nice limit. So that's how it's going to look. Okay. If you have any questions on doing 2.3 stuff, we're not going to have any 2.5 on the quiz, so we'll save that for like the next quiz, just because we just started talking about it, and I'd rather have some time in person to go over any questions. But we should be able to do 2.3 stuff there. So for that, if you have any questions, let me know. If you're working on the WebAssign stuff, that'd be pretty good to do. And as a reminder, I am taking the 2.2 paper homework on Friday, and then we are pushing the I think it was the 2.3 paper to be due on Monday with the 2.5 stuff. Okay, so just as a reminder, and I am going to go in Moodle right now and kind of change that for you guys, just so that the due dates on Moodle are clear. Okay, but again, if you have any questions, let me know. Quiz is 3 questions, so just make sure to take a look at those things. If you have any questions, let me know prior to the quiz.